second video on to about integration by parts, and this one is about breaking the cycle. Due to the nature of some integrals, by going through cycles of integration by parts, what you'll have is just this endless loop, and we need to break that, and there's some clever ways sometimes of doing that. So the aim of this video is to acquire a couple of these skills. Consider the integral of sine x cos x dx. This is the first of two examples. If we were to let u equal sine x and dv dx equal cos x, du dx would be cos x, and v would be equal to sine x. So subbing that into the rule for integration by parts established in the previous video, we'd have u times v, which is sine x times sine x, minus v du dx. So we would have sine x times cos x. And it's right here we realize, unless you're a sucker for punishment, that basically it's led you right back to the original integral. And thinking a little bit, if we persevered in this regard, we would go around in a cycle. But all is not lost. You could try and go back and set these up again, but the strategy to go for is basically a solving algebraic style strategy. Let's have a look. If we add the term underlined in green to both sides, algebraically we get two groups of that integral on the left. So two lots of the integral of sine x cos x dx. Oops, x dx. And we just get sine x times sine x on the right. Let's call that sine squared x. And the green term, of course, has been algebraically cancelled out. So we still have the integral we want to find on the left, albeit times two lots of them. So by direct reasoning, what we want to find is what exists in that line if we divide it by 2. Multiply it by half. So let's just do that. And there'll be an arbitrary constant on the end. If you wanted to be pedantic about it, you could put a constant here and a different constant there. Main thing, I guess, is that at high school level is that the constant exists in the final line. So we're sort of continuing on now in the second part of the video, solving now for the unknown integral still, but we're looking for a strategy, especially for integrals of the form e to the ax sine bx or the product of e to the ax cos bx, because they alternate due to the nature of the functions involved. And hence you can get into one of those perpetual cycles again. So let's see if we can break that, and solving things with an algebraic sensibility about it is often a way through this. Consider integral of e to the x cos x dx. Let u equal e to the x, and let dv dx equal cos x. And so from that we would have du dx still equals e to the x. We would have v equal to sine x, and so we'd proceed. I'm going to write it out in full. So e to the x cos x dx Okay, so the UV part is e to the x sine x minus the integral of e to the x. So we're doing the v du dx, so it's e to the x sine x dx. By this stage here, it might become apparent that this will alternate and go around in a cycle even if you make some adjustments. So what can we do? How else can we generate this expression and break the cycle? Okay, so that's what it's about. What's another way of generating that expression in green? Well, so I can refer back to the step. I'm going to call it equation 1. I'll be back. So to generate that green expression, another way of doing it would be to apply the rule for integration by parts to it, and just quickly we'd get those results there. So putting the results into the integration by parts rule, so u times v would be e to the x times negative cos x, so we'll call that negative e to the x cos x, minus the integral of e to the x cos x, because that's v v du dx, so that would be minus a negative there, so I'm going to change that to a plus. Now that also supports my reasoning for there must be another way when we're back at that step bar, that result 1 there of the green underline bit, it would continue in a cycle as well. Here's where the algebra kicks in now. I'm going to be applying this step, this result 2, so I'm going to give an identity. It's called amazingly result 2. I don't know where I got that from, but there you go. All these random names. Okay, so if we sub result 2 into result 1, what will we have? Now remember, the whole purpose of this was to find this integral here, which if you go back to result 1, you'll see it in the top left of your screen. That's what we're doing. Alright, let's not lose sight of what we're doing. So rewriting result 1 with 2 subbed into it, so that really means that the green underline bit can be replaced with everything that's here on the right hand side. So the green underline part in result 1 can be equated with that, so I'm going to do that. So allow some room for that. So writing result 1 with the substitution made, so we've got to write this bit in first. So it's e to the x sine x. Be careful of your minuses now. So either use square brackets or just think it through carefully. We're subtracting now, so we're up to this subtraction here. Okay, now this is negative, this is positive algebraically, so we're subtracting a negative for this term here, so that's actually going to add e to the x cos x, minusing a negative. And this one here is going to now be subtracted, subtracting a positive. So minus the integral of e to the x cos x dx. But looky here, we've got some algebra magic just about to happen again. We're looking for this integral. It's over here as well. So if we add that to both sides, like last time, we'll just get a multiple of what we want to find. Joy, because from the first example, we've got an idea of what we're going to do now. So that leaves the e to the x sine x plus e to the x cos x remaining on the right hand side. Now plus a constant, Now I'm going to call that C1 because we're going to divide by 2 now. So this is what we want to find. Okay, so remember that the goal of the question was to find the integral of e to the x cos x dx. So we've got 2 lots of e to the x cos x dx. So just by subtracting, by halving, multiplying by half, subtract nothing. Very similar strategy to the aforementioned example 1. So we're halving, that's why we've got to use a different constant. It's a little bit pedantic. Now we've also got a factor of e to the x, so we can go half e to the x sine x plus cosine x, slam the door, plus C2.